Welcome back to another episode of Dominic Does DIY. Don't forget to click subscribe and share, and thanks to all those who have subscribed and keep coming back to view the videos. If there's something I can improve on or something you'd like to see more of, let me know in the comments below. Today the boss comes in and asks for a single pole 4th row switch for some controls. The firmware guy is going to run an assist because he is working on some prototype test routines and needs to be able to cycle a single load between 4 different sources in order to test different parameters. The voltage sources are 14.2 volts, 11 volts, 9 volts, and 8 volts. The firmware guy says he has 2 GPIO to spare for this to switch between the 4 sources. You don't have to worry about break before make, as the firmware guy already has control of the load itself and can turn that on and off as needed. So we will cut the load, switch the source, and then connect the load back up. We're just doing some benchtop monitoring on a prototype for this, and I want it to run over the weekend, so try and get it done by end of day. Here's a bag of 2 N7000s and BSS 84s. See what you can make happen. So what do we need? We need 2 GPIO to select between 4 sources. We need to set up a single pole 4th row switch using the NMOS and PMOS that we have. And this switch operation has to supply one source to the load at a time. And each source cannot backfeed to feed the other sources. We have to have a complete disconnect between the sources during operation. We can use however many 2 N7000 and BSS 84s that we need. And as always, the resistors and caps are also unlimited, and you can use as many of those as you want of any value. Stop the video now if you'd like to solve this on your own. Otherwise, I'll give a solution in a second. And as always, if you come up with a solution that is different than mine, leave a comment down below or some sort of link, because I'd be interested to see how you also solve this solution. We know we have to have some arrangement only using FETs, combination of the NMOSs and the PMOSs. So first thing we need to solve is, are we able to take 2 GPIO and turn it into 4 selections? So basic computer knowledge, yeah, this is completely doable. If we just go through a truth table, we can see we have S0 and S1 coming from the microcontroller for our 2 inputs, and we can have 4 different outputs. We can have either 00, 01, 10, or 11. So definitely we can get 4 output selections with 2 outputs from the microcontroller. So this is not a problem. Now we need to consider the switch. So if we were going to use a simple PMOS switch that we would normally use to supply voltage to a load, this solution will not work in this circumstance because we had 2 requirements. 1, we were going to switch the load between 4 different voltage sources, and 2, none of the voltage sources could backfeed into the other voltage sources when the switch was turned on. So if we were just looking at this normal switch, a PMOS has something in it called the body diode, which is represented here by the 1N4148 diode. And so this would cause a problem when we actually put the 4 sources together, trying to control the 4 sources to power the same load. Let's take a look at that right now to get a better idea. So here we have the 4 PMOS switches set up to be able to feed the system. We have our 14.4 volt rail, our 12 volt rail, our 9, and our 8 volt rail. They're all controlled by 4 separate control circuits, but they all have the same output. So if we turn the 14.4 volt rail on, even though the other 3 are off, you can see that the power here will go through the 14.4 volt, touch the output, and then backfeed through the body diodes and feed each one of those rails. So this solution is unacceptable and it will not work. What we need to use here to create an electrical disconnect and isolation of sorts like this is a solid state switch. How we make this is using 2 PMOS and connecting the sources and the gates together. Then one drain is connected to the voltage input and the other drain is connected to the load. This is also a bidirectional switch and can be considered an electrical single pole, single throw switch. If you've never seen one before, they work because we know a PMOS will turn on when the gate is less than the VGS threshold. Since we tied the sources and the gates of the 2 PMOSs together, they will turn on and off together. We make this switchable by sticking a resistor between the source and the gate. If you have voltage on the drain of the switch, it passes over the body diode to apply the source voltage to control the switch. Now if we pull that control line to ground, then we have connection between the 2 drains. and you have a body diode blocking any current flowing from one side to the other when in the off position to give us our isolation. The caveat is you need to have a voltage source of higher voltage than the VDS, the PMOS, when you're trying to use this switch. We will work with one switch and control for now. This should then be a simple copy and paste procedure for the other 4 voltage levels. So how can we get the switch to be controlled via the GPIO from the micro? Well, usually to switch a PMOS, we use an NMOS because we can easily pull the PMOS to ground by controlling the gate of an NMOS with a micro. However, we have 2 inputs we have to watch, S0 and S1. To remedy this, we will use 2 NMOS configured in an AND gate configuration. One NMOS will be controlled by S0 and the other by S1. However, 75% of the time, if you remember the truth table, S0 or S1 will be 0 volts. So since an output of 0 volts will not turn an NMOS on, what we need to do is be able to convert that 0 into a 1. Right? We need to convert that 0 volts into 5 volts. So how can we do that? Well, we're going to use some driver gates. And so you can see here we got these are just some NOT gates. We're using the NMOSes to hook up some NOT gates. And so when we want S0 or S1 to be a 1, we can use those gates directly. But when we want a positive on the output being low, then we'll use the NOT of this. So you can see here in my NOT gate formation, I have an S1 and I have a NOT S1. I have an S0 and a NOT S0. So anywhere we're in the truth table where we see a 0, we would actually use the NOT of that to give us a positive value. And anywhere we saw a 1, we would just directly use that line. So now we got all the little parts. Let's go ahead and put it all together for the final solution. So you can see here, I've got my 4 voltage sources with my 14.4 volts down to 8 volts. I have my 2 gate drivers here for my S0 and not S0 and S1 and not S1. I have my control switch up here that uses the gates that are necessary for that particular one. And I got my 2 control pulses over here for S0 and S1. And all I've done is so that it can just cycle through and give us the truth table as an output. I had the S0 pulsing at 1 millisecond turn on with 2 millisecond period. And then for S1, I just doubled that. So that'll give us an output that we'll see in the simulation here that I'll run in a second. It'll give us the simulation where it'll run through the truth table of 0001, 1011. And then we can see the outputs. Just for the space of the screen, I've only got one of the control circuitries. So you can see here 14.4 volts is being run by the truth table portion of 00. I do have the other voltage references here that are connected to the system load, just like we wanted. And you can see here that 12 volts is controlled by 01, 9 volts by 10, and the 8 volts by 11. So as we go through the truth table, we should see on system load the change in the voltage output going from 14 volts to 12 volts to 9 volts to 8 volts. So now let's go ahead and run the simulation and see how it looks. So you can see here the S1 and S0. You can see how it goes from 00 to 01 to 10 and 11. And likewise, you can see our system load output. It goes between 14 volts, drops to 11.1 volt, drops down to 9 volts, drops down to 8 volts, and then goes back up to 14.4 volts, just as we expected as it's going down. So now all we got to do is verify that we don't have any backfeed of voltage onto the other sources. So we know that it works the way we want it to with the output changing voltages, but let's make sure that we don't backfeed into the voltage sources. So what we'll do in order to test the backfeed action is because we know that the backfeed is going to happen if voltage on one side on the load is going to be greater than one of the other voltage sources. So we'll just pick the 8 volt one because that is the lowest one. And all I'm going to do is I'm going to stick a resistor right in line with that 8 volt source. And I'm just going to make it really small. We're going to go with like 0.01 ohms. And why 0.1 ohms? I'm just trying to create a voltage differential between the voltage source of 8 volts and the one side of the MOSFET, right? The drain of this MOSFET where it's sourced at. So if any backfeed voltage comes in where it says V8P0, I'll have 8 volts down here where the source is, but if anything backfeeds, I'll have a higher voltage up here, and then I should be driving current through R7 back into this energy source. But I can basically just take a voltage reading on this point right here, and then that'll tell me if I've got any backfeed voltage coming through the system. So let's go ahead and run this one more time, and then we'll just take a voltage reading at this point on the resistor. And so you can see, it looks like there might be a spike, but this is just all smoke and mirrors, because if you look over on the left side here, I don't ever move from 8 volts really. It's just the window is really small. So I'm just seeing some weird anomalies happening right now because of the switching circumstances. So we can absolutely see that we're getting no backfeed action with this circuitry here. So that's it for today's episode regarding the solid state switch. And I hope you had some fun and enjoyed it. And like I said, if you came up with a different solution than this, please put it down below. I'd be interested to know what you came up with. But until next time, remember, doing stuff is the best way to go from sucking to getting good. So keep on doing stuff. And until next time, have a good one.